I will talk a little bit about novel methods for producing ammonia. I'm a PhD student in Vidar Jensen's group. My co-supervisors are Ervan, Giovanni, and Marco. So firstly, I would talk about, say, ammonia in general. So today it's produced by the Haber-Bosch process, where dinitrogen and hydrogen are combined at very, very high pressures and very high temperatures using say a heterogeneous catalyst in order to produce ammonia. Say about 185 million tons of ammonia is produced per year. So this number is from 2021. And this is responsible for about 2% of the total carbon dioxide emissions worldwide. And the main reason for this is that the hydrogen you use come from the steam methane reforming reaction. So we are using natural gas to produce the hydrogen we put into this reaction, which also is an issue. Nature, however, have developed enzymes that can do this at, say, ambient reaction conditions. So we only have 1 atmosphere pressure, and then they do this at room temperature. And here they also take dinitrogen from the air, and then they have some electron or reducing agents in form of as parts of the enzyme, and then they use water as the source of protons here. And then they can combine these and produce ammonia. And these nitrogenases are much, much faster catalysts than the heterogeneous ones in the Haber-Bosch process. Another, say, promising thing with ammonia, which is already used as a fertilizer today, is that, say, compared to hydrogen, so hydrogen is easier to make, but it's highly explosive and it has a low energy density. So it's, say, it will take up a lot of space in order to pack enough energy to do long trips. And it's difficult to liquefy in order to make it more compact. Whereas ammonia has an existing infrastructure, it doesn't explode. And it has a higher energy density, and it's also easy to liquefy and store. And then we also have this fertilizer usage, which is already very important. So I work with what we call homogeneous catalysts, which are these molecular complexes that catalyze these types of reactions. And there have been a lot of development on these in the last 20-something years, where they use, say, a metal catalyst combined with a ligand. So, for example, we have this PNP here, which is a ligand. And then they combine, or you can combine these using this pyridine derivative as the source of protons. So this proton here is given away to ammonia, and then you are adding, say, an external reductant, which reduces. So this is the source of electrons. And these are, say, catalytic systems that are inspired by these nitrogenase enzymes. However, in, say, none of these could do this with water as the proton source. So you always needed some stronger acid to do this. And here one is able to produce about 10 to 100 equivalents of ammonia per equivalent of catalyst. So say each catalyst on average produces between 10 and 100 molecules of ammonia before it dies. In 2019, a Japanese group published this result where they combined dinitrogen with samarium diodide and water, and then they could produce ammonia in extremely high yields. And you can also see that the turnover number here, or the equivalence of ammonia per molybdenum catalyst, is bumped up by an order of magnitude. And they are, so the catalysts they're using are these two here. Say either of, especially the catalyst here on the left, catalyst 1, is also extremely fast. So it's actually faster than that of nitrogenases. There are, however, some, or I should, yeah, So these catalysts, so when we work with, say, exploring catalysts, we work with, say, what's called a reaction mechanism. So it's a way to represent what's going on inside the reaction mixture. And these catalysts are proposed to follow a so-called cleavage pathway, where the dinitrogen from the air is coordinated to the molecular molybdenum complex, which then dimerizes and then cleaves the nitrogen-nitrogen bond, yielding this molybdenum nitrido species with a triple bonded N. And then what this is reduced and protonated to give ammonia. And that is one of the reasons why this reaction works so efficiently. And another reason is that the combination of samarium diodide and water gives us a strong proton-coupled electron transfer agent, which directly transfers a hydrogen atom instead of say or stepwise protonation and reduction. Yes, and this also gives, say, as a source of the increased activity of the catalysts. However, I mean, this system is not perfect. So, say the atom economy is absolutely horrendous. So you're using 6 molecules of samarium diodide to each molecule to 2 molecules of ammonia. So one needs to find a way to regenerate this samarium. And also the catalyst is deactivated, so we would like this turnover number to go above millions. And then there's also another issue, and that's the release of ammonia, because this reaction is take place in solution, and ammonia will dissolve in that solution. So we need to find a way to release it afterwards, so we can actually use the free ammonia we need. So say the overall project has 2 objectives. So we need to say make more stable catalysts, but also maintain a high activity. So we want this turnover number to be above 1 million. And then we also want to, say, replace or still use samarium diodide, but regenerate it, to use electrocatalysis to do this. So the idea here is we take air and then we use renewable electricity, and we get protons from the air and the water, and then we have a catalyst that will catalyze the process of making ammonia. And I will tell you a bit more about, say, the first one here, which is what I work with. So our approach is so we want to establish an accurate computational protocol for the reaction system. I will come back to say what this computational chemistry is later. And we want that because we want to understand exactly what's happening inside the reaction mixture. Because then we can understand what chemical properties that a good catalyst has, and then we can use those properties to develop more stable but also active catalysts from, say, more cheap and sustainable materials. So as I mentioned before, there's a large difference in catalytic activity just between these 2 catalysts here. So I'll just briefly go over computational chemistry. So say one of the tools used in computational chemistry is called density functional theory, which is abbreviated DFT. And we can use DFT to gain insight and understand what's going on in the reaction mixture. But say DFT is an enormous toolbox, so it can be difficult to pick the right tool. And we need results we can trust, because we need the properties that we are, say, chasing to be accurate and reliable. So we have done, say, a validation of the DFT method we are using. So I have a slide on this here. So we have found an, say, accurate computational protocol. So for example, the samarium 2, samarium 3 redox couple here is very, very difficult to model. And we have published a paper on this last year. And we have also, say, found a computational model or protocol that accurately can describe both the samarium 2, samarium 3 couple, but also, say, molybdenum in various oxidation states. Yes, so let's move on to trying to understand this reaction. So the catalyst, so this is a little bit nicer scheme than what I showed you before. But the pre-catalyst is added to the reaction mixture, and then it's rapidly reduced to form this molybdenum bis dinitrogen species. And then this species dimerizes, forming this dimer, where the terminal or the bridging dinitrogen is cleaved, yielding this molybdenum 4 nitrido species. And here, say I'm going from this point to here is very, very easy. And so what we call is the rate determining step is the subsequent step. So reducing and protonating this one to gain to get this one. So this step has the largest barrier, which is the hardest to do. And also the DFT protocol we have produced is producing, say, experimental observations. So we can reproduce numbers from the experiments using this protocol. So we also know that it's trustworthy what we are finding here. So I've just plotted the reaction-free energy diagram of these proton-coupled electron transfer steps. So we can see that we have the molybdenum 4 here, nitrido, and the largest barrier is going up, getting to this molybdenum 4 imido, and it is for both of the catalysts. And there's a large difference between the barriers. So for the blue line, which is this carbene-based catalyst, the barrier is 15.1 kcal per mole. The experimental is 15.2. And for the other one, it's 18.8. So it's much higher. And this explains the difference in catalytic activity between the two catalysts. Yes, so now we know what's going on in the reactions system. So, and we also know from Marcus' theory that if we reduce the reaction-free energy, so say the size, so the difference between here and over here, we will also reduce the barrier. And we can do this by stabilizing the product of the reaction. So we want to stabilize this side and preferably destabilize, or at least not stabilize this part of the reaction, or let's say the reactants. And we can do this. So what the best catalysts do is that they do this by orientally restricted pi acceptance, which heavily stabilizes the product, but does not stabilize the reactant. And that leads to very, very high catalytic activity. So I've plotted something here. So now for the best, say, catalyst framework, where the pi acceptance is restricted. So there's a lone pair, so 2 electrons on the molybdenum, which reside in these orbitals here. And then there's a pi accepting orbital here. So this orbital, these orbitals are empty, but so you can distribute electrons from the molybdenum to this lone pair, or no, lone, say, empty orbitals, and then so in this case, there's no overlap, and therefore there's no pi acceptance. So we are not stabilizing the reactant. However, when we add the electron to the system, these electrons are perfectly aligned for pi back bonding, and we will stabilize the products. So by having the, say, pi accepting orbitals aligned perfectly, one can stabilize the product and not stabilize the reactant, and thus reduce the reaction-free energy and then the barrier. So we have a more active catalyst. And then I have an example here where we have, say, non-restricted pi acceptance. So we are allowing say, the pi accepting orbitals here to freely orient itself in a way. And here we see that it perfectly aligns with this lone pair on molybdenum. So we are stabilizing the product here, and we are not doing anything. No, we're stabilizing the reactant, and we're not doing anything for the product. So we have a very stable reactant, unstable product, and we will have a large reaction-free energy and a high barrier. So the next point was to use this knowledge to create new catalysts. So this catalyst I have created here should have a very low barrier for the first proton-coupled electron transfer step, because it has a very low reaction-free energy for this step. And the plus with this ligand is it's super easy to synthesize, and it's also very cheap. And furthermore, the ligand here should bind stronger to the molybdenum, which means it's less prone to decompose. So I made this and I tried testing it, but it was very bad for catalysis, and that's because the rate determining step is moved. So instead of being, say, the first proton-coupled electron transfer step here, it's moved to somewhere in this dimer formation. So, and this goes to say that one really needs to understand all the components in the reaction when we're modeling, if we want to, say, develop more active catalysts. Well, a few conclusions here. So we have produced a computational model which is in great accordance with experimental data. So we know, say, the main reaction pathway for ammonia production inside the reaction. And this orientational restriction of pi accepting orbitals is essential for high catalyst activity towards ammonia. And then for future work, it is good to know that we need this combination of samarium diiodide and water, because we need these PCET pathways, or proton-coupled electron transfer pathways. And we have synthesized a new catalyst and tested it, but it has poor yields due to problems in this dimerization step. And we are doing work on designing new and making new catalysts that should not have this problem. And then what we also want to, say, figure out in the future is understand how the catalyst decomposes or how it breaks apart. Yes, I would like to thank the Research Council of Norway for paying us, and my supervisors for helping me out, and also Leif, which is my colleague who's also working on this project. So, yeah, thank you.